Hello everyone, I'm Denis. I'm making my own CPU based on standard logic ICs and some simple gates and logical circuits like AND or multiplexers and so on and so forth. And I have already built my own instruction set architecture, so I'm building an 8-bit CPU with a stack architecture, so I don't have the classical register file, but I have a fixed stack. I've already built my own toolchain consisting of a simple emulator and assembly tool that allows me to convert my code from a human readable format into the binary. And now it is time to start working on the actual hardware. It is time to start working on the design of my CPU. And I'm going to start with the arithmetic and logic unit today. Maybe one of the simplest units, but funniest ones, and I really like building ALUs. So I'm going to build my ALU with a logisim. I have kinda 8 instructions to implement. Well, I have 9, but I will explain why I'm not going to implement multiplication right now. Anyway, we need to start with the logisim. Logisim is an open source circuit design and simulation hardware that allows you to build your logical circuits and check them. So I'm going to use the logisim as my primary tool for design and testing my design. I'm using it first time in my life, so I could be a little bit disoriented with it, but still should be fine. Well, my first command of my CPU is add, and this means I need to start with an adder. And how do you implement an adder for CPU? How does it work? Let's think of just a simple adding. Let's think of like taking two numbers like 103 for example and 98 and adding them together. So how do we add them? We take each number, like each digit of the number, and sum them together. So 3 plus 8 is 11, we carry 1 and write 1. 0 plus 9 is 0, plus 1 is 10, so we carry 10 and write 0, and finally we have 1 and carried 1, so it's 2, 1, 0, 1. The carry part is interesting because we always carry just 1, so even like 9 plus 9 gives us 19, so we always carry just 1 to the next digit. The same applies for the binary logic. If we add 0 plus 0, we get a 0. If we add 1 plus 0, we get surprisingly 1. 0 plus 1 is obviously 1. And finally, if we add 1 plus 1, we get 0 and 1 as a carry flag. But it is better to write this carry flag on the opposite side, so it will be more reasonable. Actually, from this table, we can build a kind of truth table. So we have an A and B operands, we have a carry flag, and we have a sum, like the result of the operation. And this is the truth table. Having this truth table, it's pretty simple to make an adder circuit for it. Because like if you have a look on the truth table for the carry signal, you'd see that it only becomes true, like 1, when you have A and B 1. So that's logically AND gate. For the sum, it only becomes 1 if either one of the arguments is different. So it's either 1, 0 or 0, 1, which is the truth table for XOR. So obviously you can use a XOR gate to produce a summary. And this is how you build an adder. And this is how you build a really small adder for just 2 bits. But we call it a half adder. And why do we call it a half adder? Because we need to handle incoming carry. This one just adds A and B, but I need to somehow propagate carry from the previous bit to the next bit. For this, I can combine 2 half adders into a single full adder, which is like just 2 half adders. But first let's try to write the truth table for the full adder, and I really like full adders because they are fun. The full adder takes 3 arguments, like 3 bits. It takes A and B operands plus carry in flag, and it outputs carry out and summary. Obviously for all zeros, it gets all zeros. If you have just one bit set, it's either A, B or carry in, you will get just the 1 in summary. For 2 bits, you will get the binary number 2, so you will get 1 for carry out and 0 for summary. And for all 3 bits, you will get both carry out and sum set. So technically, full adder acts as a bit counter. This is the thing that I mostly like in it. That's not an adder, that's actually a bit counter, but surprisingly, that's an adder too. I'm not going to discuss how to produce the full adder from the full truth table, because obviously I don't want to spend my time just writing the whole truth table. But this is pretty simple. As I told you, we need just 2 half adders, so adding A and B plus adding the carry flag back to the result of A and B and checking if carry condition happens. Let's go back to the OJSIM and start with our first circuit. I'm creating the first circuit, 1-bit adder. It will get 2 inputs. It will actually get 3 inputs like A, B plus carry in flag, and there will be 2 outputs, summary S and carry out. And now I need to put my adders, so I need 2 OR gates. I need 2 XOR gates, I need 2 AND gates, and I need 1 OR gate to check if carry condition happened. Each pair of XOR and AND is a part of the half adder, so like for adding the A and B or adding the C in, carry in to the result of the previous summation or adding. And finally, the final OR will tell you if carry condition ever happened in one of those adding operations. And this is it. That's really all. That's pretty simple. That's how it looks, the full adder. And the thing that I like in the LogicSim, you can immediately try your circuit. So you can switch into the simulation mode and start checking what will happen if you change the input. So you see, in my case, I'm switching like bits and I'm getting the expected result. Because with the full adder you only have 9 invariants, so you can just click all of them and see if it goes correctly. For a more complicated circuit you need a more complicated approach, but this one works for now. Okay, having a 1-bit adder, how do we make a 8-bit adder? Let's make a new circuit. I will need 2 inputs. I don't need to have a carry in input now, because I'm not handling like long summations, long additions, so I need 2 inputs, A, B and some output, and both A, B and some output, they need to be 8-bit wide. This is pretty simple, like 8 bits wide means there will be 8 wires, but for brevity it looks like just a wide wire or like wide value in the LogicSim. And then I will need 8 1-bit adders, so I can copy them like one by one. And after this I need to split my input into bits. This is not a logical operation, because as I told you, the 8-bit input is actually 8 wires, but here, because of the brevity, we need to split those wires into the bits. But in the hardware we don't need to split them. And then we need to connect all the A bits to the corresponding inputs of 1-bit adder. Same for B input, they go to the corresponding bits of the 8-bit adders. Finally, I need to do exactly the same thing on the opposite side. Gather all of my 8 bits of result into a single 8-bit number that goes outside of my adder, so that will be kind of reverse splitter, which I connect to my output. That's almost it, but I have one thing that it's not done yet. The first carry in is not connected. I will connect it to just 0, because I don't have any input from the external carry, and then I will daisy chain carry outs to the carry ins of the next following adder. So if the carry carry event happens on the summation, it will be propagated further. And last carry out is just left unconnected. This is the simple, really simple adder, but it has one problem. The thing is, when we speak of electronics and when we speak of electrical circuits, we usually think like, hey, when you change something in your input, the output changes immediately, like instantly. In fact, it doesn't. And fortunately, LogiSim allows us to see this, because if you change something on the input and then you do step-by-step simulation, you will see how your changes in the input are actually propagated. So you first see the input of the gate is changing, but okay, that's wire, so we can actually avoid this and don't think about that. But then output of the gate changes and input of the other gate changes, and so on and so forth. The thing is that when we change something on the input of the gate, the change on the output doesn't happen immediately. It happens with some delay, and we call it a propagation delay, which can be pretty significant. For example, I'm going to use low power ICs, and they have propagation delay of roughly 20 nanoseconds. So each gate will get updated in 20 nanoseconds. And the signal in my case passes through the 3 gates, and this is my critical path. So the critical path is the longest path on the signal update. In my case, it's like XOR and OR elements for carry out, from A to carry out. So my my critical path is 3 gates, and my propagation delay of the whole adder is about 60 nanoseconds, which doesn't sound too much. But what if I connect my adders in a chain? I'm going to have a ripple carry adder, and you have to wait, like first adder after 60 nanoseconds gives you a C-out signal. Then you have to wait for the second adder, and so on and so forth. So in total you get 60 times 8, roughly 500 nanoseconds delay in this adder. And this is disadvantage of a ripple carry adder. The reason why I'm choosing this one adder, because it's pretty simple and it requires, I would say, minimum of hardware. It requires 1/4 of quad OR gate circuit and half of quad XOR circuit, half of quad AND circuit. So in total it will be, I think, 10 ICs for the whole adder. But the price I'm paying is the really long propagation delay and the huge and long critical path. There are better options. There exist better options that can give you a smaller propagation delay. They can give you, they do most operations in the beginning, but unfortunately, they require more hardware. But anyway, what about subtraction? I'm going to implement subtraction with the addition. And you will probably think like, what? How is it possible? Well, there exists a neat trick that will allow me to do this. When you would like to, say, add a number, like you say 6 plus 3, you get a 9. What will be the number if you subtract 3 from 6? 6 minus 3. It will give you 3. But what if you add minus 3 to 6? You will get the same result, which means if you add a negative number, you can implement a subtraction with addition. The question is how to get a negative number. Fortunately, we are operating not in a normal number set, we are operating in a ring of numbers. And this is simpler to show on the watch display example. For example, we have 6 and 3, and we have that round display that wraps over 12. If we go anti-clockwise, minus 3, we will get to the 3. But if we go clockwise, 6 plus 9, we will wrap at 12 and end up in the 3. So anytime you need to subtract something, you need to split your display in half and find an opposite or complementary number. For example, for 3 it will be 9. If you would like to do 6 minus 3, you think, okay, I need minus 3, the complementary number is 9, so I need to add 9 to 6. And because we are in the ring, so add 9 to 6 will not give you 15, it will give you actually 3, because you wrap at the end of the ring, you wrap at the 0 or 12. This works. You can check that it works with all the numbers, and it works in both directions. You just pick up the complementary number and add it instead of subtracting it. But this complementary number in the ring of 12. What if we have a binary number? For binary number we have a really nice thing known as 2's complement, and I'm not going to give you any scientific proof how it works, but I will give you just an algorithm. If you need to find a complement number for the binary number, you have to invert all the bits and add 1. So it's operation of inversion plus addition of 1. With this knowledge we can start building our sub-circuit. So I will start with adding a new circuit, add sub, the same inputs and outputs, like it will be A and B operands, 8-bit byte each, same for the output, which is not a sum anymore, so I will probably call it just out. And I will need a adder. Yeah, I can't call the out because that's a reserved word in VHDL. So let it be result. But then I will need an adder, and I'm not going to actually invert the result, but instead I'm going to use the feature of XOR gate. XOR gate can act as a NOT if you set one of the inputs to 0, or it can just pass the signal if you set your input to 1. Unfortunately, it doesn't work the way that I wanted, so I have to split my B signal again and then combine it after the set of XOR gates. And my second input for the XOR gate will actually be a control input. What if you have both zeros on both inputs? You will get a 0. What you have 0 and 1 coming from other input, you will get a 1. But what if you have 1 fixed on one of the inputs? If you get 0, you will get a 1, so now it's inverted, and if you get a 1 and another one input in 1, it will be a 0, so it gets inverted again. So that's how it works. And by switching one of the inputs from 0 to 1, we can control if the XOR gate is passing the signal untouched or negating it. So we decompose our signal back to bits, pass through our programmable or switchable negation network, and then combine it back to the 8 bits and connect it to the 8-bit adder. So this gives me the summation plus negation. What about plus 1? I will handle plus 1 in a very interesting way. What is a plus 1? The plus 1 means that you actually have one bit on the right side of your number. Or we can think about it as you have a carry in bit. So I need to extend my 8-bit number with a carry in acceptor. So for this I need to remove my constant number and add another one input. That will be just a single bit input, carry in. Let's call it C in. So I connect my C in to the first carry in my ripple carry adder, and after this I can connect my carry in to the control bit of my subtraction circuit. So when it gets 1, XORs are going to negate my B operand, plus this control 1 will also act as a carry in for my adder, thus making the B operand 2's complement number, thus making it a subtraction instead of addition. And this is how you build a subtraction with a addition in the binary world. So that's subtractor. The next operation that I have on the list is a multiplier. The multiplier is a tricky thingy. How do you multiply? Like, multiplication rules for the binary numbers are exactly same as for the decimal numbers. You have two numbers, multiplicand and multiplier, and then you start multiplying your multiplicand by the rightmost digit of the multiplier. Then you take your multiplicand, shift it to the left, and multiply to the next digit of the multiplier, and so on and so forth. And at the end, so you're getting those intermediate results, and at the end you sum all of those results and get a number. Binary multiplication, actually, yeah, this is absolutely correct for both binary and decimal and any system, but binary multiplication has a couple of special rules. The first one, if you multiply 4-bit number to 4-bit number, you will get 8-bit number. So the number of output bits is doubled. For 8-bit numbers, you will get a 16-bit output. For example, for addition, it's always +1. So if you add 8-bit numbers, you will get 8 plus 1, 9 bits. 8 bit of result plus 1 bit of carry. But for the multiplication, it will be doubling. So for 8 bits of operands, you will get 16 bits of the result. Second one, if you pay a closer look, you will see that you're actually just shifting the multiplicand to the left all the time, and shifting the multiplier to the right all the time, and checking if the multiplier rightmost bit is 1 or 0. So if it's 1, you put your multiplicand. If it's 0, you put zeros. This makes multiplication in binary simpler. This makes it simpler to implement. You don't need to actually multiply numbers. You only need to check, you only need to implement a couple of shifts and check if you have 0 or not. And this allows you to make a rotating shift, rotating multiplier, if I can say so. Like having a couple of shift registers for A and B, having a multiplexer that will either send the copy of A if B is current rightmost bit of B is 1, or just will send a 0 to the adder, so no operation. Plus you will need a register for intermediate result, and you update your register from the adder until you run out of bits. This is pretty simple and very effective scheme. And you don't need too much hardware for that scheme. The only problem is that you need 8 cycles. I mean, for 8-bit number you need 8 cycles, which is not the thing that I would like to have. Why? Because my CPU is non-pipelined. I don't have any delays. If I will have to wait 8 cycles, I need to store everything else. I need to somehow stall my CPU. Because of that, I'm not able to implement this kind of multiplication. Another one option will be to unroll it. Like, what if I make a hardware that will do the first intermediate result? Like, get the first number from multiplicand and check if the rightmost bit is 1. Then I can make a second set of adders for the shifted rightmost bit of multiplier and add it with the result of the previous operation but the shifted one, and so on and so forth. This will give me, for 8-bit numbers, I will need 64 adders plus 64, I think, AND gates. Yeah, and this is not 8-bit adders, by the way, that's a full adders. But still I need 64 full adders, plus I need 64 AND gates, and so on and so forth. Plus I will need a lot of hardware, because that's more than 64 ICs on a board. That's too much for me. Plus the propagation delay will be in milliseconds already, because it will be like 500 milliseconds times 64 plus ANDs, so no, I'm not going to implement it. Instead, I will go to the other operations and I will start working on my ALU. The ALU is connected to my X and Y registers all the time, so this time ALU will get X and well, that will be x in and y and x out, because the results of the ALU operation goes to the x register too, so that's x in and x out. I will obviously need an adder, because I already added an adder, and I will connect A and B to it. And then I will implement shift operations. The shift operations are pretty simple. You don't need any logic. You just connect your input and output with a single shift. So if that's a left shift, you like skip, well, on the left shift, yeah, you skip the rightmost bit and set it to 0. And for the right shift, you skip the leftmost bit and set it to 0. And that's just the wires. You don't need any logic here at all. This is really simple. The only trick is that, okay, I have left and right shifts. So I have two splitters. One for the left shift, well, that's more like a combiner, like anti-splitter. One for the left shift, one for the right shift. And now I need to choose a result. How do I choose a result? Well, there's a special logical unit known as multiplexer, and you can also buy that IC multiplexer that takes two 8-bit inputs. Well, that's in my case an 8-bit inputs. It's not just 8-bit, but yeah, it takes 8-bit inputs, like left input and right input, or A and B, and a single control bit. And with the single control bit, you actually choose which input you would like to connect to your output. So this is your control input in my case. I will put a multiplexer connecting like left and right. I will connect the output of the multiplexer to my result, and I will set a new one input, like new one input connector or input pin, left or right, that will actually control the multiplexer. And that's how you build a shifter. Well, there also exists a barrel shifter that allows you to shift random number of bytes, but in my case it's just one bit left and one bit right. And this is it. Now I have a shifter, left shift and right shift, and it works, so I can go back to my ALU and integrate it. The shifter is just an unary operation, so I only connect it to the X in. Okay, then I have operations like XOR, OR, NOT, AND. They are just logical operations, so I will use the gates for those operations. I need to pull the respective gates, and I need to connect the respective gates to the inputs of my ALU, to X in and Y. Obviously, I need to connect them to the output. So how do I connect it to the output? Because I need to select what will be the output. First of all, I can use a set of multiplexers. So I have 6 operations here. I can build a tree of multiplexers, like for each pair. Then I will put more multiplexers to pick up from the pair of multiplexers, so on and so forth. I can do this. I don't think it's possible to buy multiplexers bigger than 2 8 ports to 1 8-bit outputs. Okay, they wouldn't be comfortable to work on, but the problem is that I'm going to have a pretty big propagation delay, because I'm going to have like 3 multiplexers to pass. Instead, I can use a controlled buffer, or like a bus buffer. And the bus buffer is an IC that just passes your signal from input to output. And it also has a control switch. So if you allow it to pass, it will copy input to output almost instantly with some propagation delay. But if you don't allow it to pass, the output will be in high impedance state, which technically means it's just disconnected from your wire. I would also like to keep my bus. Yeah, I think I will keep my latest output multiplexed, because I want my add sub to be a default value, but maybe I can change it later, I don't know. So finally, having those buffers and multiplexer, I can start adding new input ports, like for all the operations, like for add, for sub, like both add, sub trigger the multiplexer, that's why I need OR gate. Same for left and right. Yeah, I think right controls it, and same OR, and if either left or right, I need to trigger it. For the rest, it's just an input port, so it's pretty simple, and I will get 8 input ports. And this is almost it. I'm connecting all the ports, so now I have my 2 inputs for both operands. And now I have 2 inputs for my operands. I have control ports, and with each control port I can pick up which operation will be on X out. The last thing that I would like to do is that I would like to decrease the number of control ports, because like 8 ports means I'm going to have 8 wires. But do I need to pass 8 wires for value of 8? No, because I can use the special logic circuit known as a decoder. And decoder takes a binary number in 3 bits in my case, so it takes just 3 bits, and it has 8 outputs, and it will enable the output encoded by those bits. This way I can have 8-bit control circuit, like I can have 8-bit to switch my buffers, to switch my multiplexer, but I will only pass 3 bits to my circuit, so just 3 wires, and this will make my life much easier during the circuit design stage, because this is like a logical and I will have some physical design stage. And this is it. With the final port, control port, I have my ALU done, and that's all. That's how you can build a simple, really simple, basic but still functional ALU. And actually this ALU is a good example of why hardware acceleration is the thing, because as you can see, my hardware works at the same time. I'm doing shifts, I'm doing all the logical operations, I'm doing addition in parallel at the same time, and I just choose which results to pick. So for example, if say you need to do several operations one by one and they are independent, on the CPU they will be executed one by one, but in the hardware you can implement them in parallel, and then they will happen in parallel, and then you can use them, they result almost instantly. That's why hardware acceleration works. And actually in the modern CPUs you can use your hardware in parallel. For example, let's imagine you have a one execution thread that requires add sub, like it requires adder, and another one thread would like to make a condition, so it needs an AND switch. With a lot of wiring, with some special control logic, you can actually share the ALU and say like, okay, the thread number A gets just an adder and the thread number B gets an AND element. That's actually what hyperthreading means. It's not a separate execution core, but it's like sharing the unused parts of the execution core between the threads, between the programs. And this also explains how the power saving works, because yes, all of my hardware works in parallel, but I may not just pick up the result, but I can also turn on and off my hardware units if I don't need them and save some power. But my CPU is pretty simple, so I'm not going to do this. Instead, on the next stream, I would like to continue working on my stack, and this will be at the same time more complicated and maybe more interesting, because I'm going to have some clocking, I'm going to have some state and state machines. So, thanks for watching and see you on the next video.